If you have any questions throughout any of the webinar, please feel free to type them in the questions panel on your dashboard. I will leave some time at the end of the webinar to answer any questions that you may have. Everyone that registered today for the webinar will receive a printout of the slides and also a link to the recording of this webinar later this week. If you missed anything or anybody else wants to see the webinar, we will have a recording of this webinar on both our Exida YouTube channel and the Exida website. Today we're going to talk about safe failures or spurious trips and why they matter to you. So it is important that a plant does not encounter spurious trips, therefore disrupting the process and losing time, which results in losing money. Even more important is preventing the occurrence of an accident that could result in a loss of the plant or equipment. It could result in damage to the environment or even loss of life or human injury. This webinar today will discuss how calculating the spurious trip rate is important and what can be done with that number and how you can use that to save time, resulting in saving money. It will also cover dangerous detected failures and how those play a part in the safe failure fraction calculation and how they are compared to spurious trips. We will also look at how a simple mechanical device or final elements can still partake in SIL ratings, and we're going to investigate the 2H method of evaluation without adding additional safe failures to be present. Just quickly about me, my name is Loren Stewart. I work at Exida, mostly with our mechanical customers. I do safety consulting and auditing, FMEDAs, along with doing some alarm management and end user work and research in mechanical failure rates and stiction and the 2H initiative. We have offices worldwide, so no matter where you or your customer is, we have someone close by that can help you with all of your functional safety needs. We can be easily divided up into main product and service categories, but the underlying theme is functional safety. So no matter if it's functional safety with the process or the products of functional safety or being trained or taking your personal certification, CFSE or CFSP, that would be the people, as long as it has to do with functional safety, we play a part in it. We do consulting, we have our engineering tools, we have our product certification and our training, we have our reference materials and books and white papers, as well as our professional certification. After a product has gone through the full functional safety evaluation for IEC 61508 or our cybersecurity certification as well, your end result is a certificate. And this is what an example of the front of the certificate looks like. On this certificate, there's a lot of good details, and on the back of it, we will be talking about some of the failure rates and what they mean on the back of the certificate. Exida has established a scheme for functional safety and cybersecurity certifications of systems, of products, of components, and of personnel. The functional safety certification involves a detailed analysis of both the engineering process and the design margins, resulting in random failure rates in all failure modes. The cybersecurity certification involves a detailed analysis of engineering process, the cyber defense mechanisms, and the network robustness. This is just a few of our reference materials that we have published that we're really proud of. We like to say that we are a complete open book. We don't like to hide anything. We feel that the research and our process and everything that we do can make the world a safer place. So we like to be completely transparent. So if you have a question on some of the research we are doing, we will have white papers that show exactly how we did our research and what we've learned. The books have the process of the FMEDA. We have our database in the SCRH handbooks. So everything that we learn and we study, we publish. So for the reason why you're really here today, safe failures aren't always your best friend. We're going to break up this webinar into a few different topics. We're going to start with looking at if safe failures are friends or foes. We're going to look at the pros and cons of safe failures. Then we're going to look at how to use the safe failure rates to your benefit, what dangerous detected failure rates, what that really means and how that can affect your plant. We're going to look at calculations using safe and dangerous detected failure rates, how simple mechanical devices or final elements can still participate in a SIL rating with either low or no safe failures. And then finally, Route 2H. What is it and who should use it and how? This topic of this webinar all started when someone came up to me at a trade show and say, "Oh, we don't like your type of work." So of course I smiled at him and I asked him, well, why is that? He started to vent to me. He started to tell me his story about how his plant is shutting down so often, he's losing money, so on and so on. It was his idea that functional safety meant him losing time and thus losing money, and that Exida and other functional safety companies, we want spurious trips to happen. In his eyes, we were the bad guys. We were causing his spurious trips. We were causing him to lose time. We were causing him to lose money. So I kept the smile on my face and I told him that at Exida we don't want you to have safe failures. He was pretty surprised. I said, we don't want to shut your plant down. We don't want you to lose money. We don't want any of that to happen to you. But we really don't want dangerous failures. We really don't want an explosion, or we really don't want a toxic leak, or we really don't want people getting hurt, or possibly even worse. So yes, spurious trips are not our main objective. Our main objectives is preventing the very bad things from happening, but we don't want spurious trips or safe failures to happen either. So working together, we can prevent dangerous failures being the first priority, but we can also make sure we prevent spurious trips as well. So as you can see, like almost everything in life, safe failures can be broken up into pros and cons. The good thing about a safe failure is that it helps your safe failure fraction, and we'll look at the equation and what that really means later on in the webinar. It shows that your system is working properly. If you have a spurious trip and your gate valve closes, you know that it's not going to be stuck in the open position. You know that it can do its job when it's needed. And you're trying to look at the glass as half full, it's better than a dangerous or even an undiscovered failure. The negative is that it shuts your process down. That can be annoying, getting the process up and running again. It loses time, and losing time is losing money. And you have to document why this spurious trip occurred and investigate why it happened, how it happened, and see what to do so it doesn't happen again. And taking the people and the resources and the time to document it and the investigation also causes loss of time and loss of money. And so that's not what we want. An example to look at is one of my coworkers was on a plant tour, and they noticed that a system was completely bypassed, one of their safety systems. And of course, that's a huge red flag in our eyes. So he asked, well, what's going on here, and why is this going on here? What's going on? The plant manager simply said that they have too many spurious trips, they couldn't deal with it, so they came up with a solution. And then the solution in their eyes was to completely bypass the safety system. And unfortunately, this happens more often than anyone would like to really acknowledge, especially in the functional safety world. Sometimes it can be a simple bypass like rewiring something or pulling wires out. Sometimes it could be bypassing by they get some piping, route it around, or route or pipe through, or sometimes it actually, once we saw it bypassed by a piece of wood actually, and they just stuck the piece of wood in the gate valve and it prevents it to shut. And yes, I guess that's one way to make a gate valve stay open. Is that the best way to make it stay open? Probably not. I'm sure that there could be a million better ideas, but it happens. And if you have your spurious trip rate too high, it's something that operators don't want to deal with. It's something that plant managers don't want their plant shutting down, and they could be bypassing a safety system, which could result in a very dangerous situation occurring and a safety system not being there to help out. So we want to use failure rates for your benefit. And doing so, you can calculate the safe failures from FMEDA. You can get your safe failure rate, both detected and undetected, and you can use those numbers to lower safe failures by changing system architecture. So you're a 1 out of 1 system. You can play with advanced modeling tools such as Excellentia and see what maybe a 1 out of 2 system or a 2 out of 3 system architecture would change, and see how your mean time to fail safe and your PFD average and everything will change when you do simple changes in the modeling software. And then you can also use that safe failure rate to find and lower the mean time to fail safe. The next portion, which is just as bad as a safe failure, is a dangerous detected failure. So your system shuts down from a dangerous detected failure. That's awesome. You detected the failure, it was going to be dangerous, it shut it down in time. That's great, congratulations. But your process is still shut down, you're still losing time, you're still losing money being down. Once again, you're going to have to document the failure and investigate why it happened. This time, with it being a dangerous failure, it's going to probably be a further investigation or a more in-depth investigation. It's more important that you investigate why. And you also need to figure out how this will not happen again. What can you make sure you do so that you don't have a dangerous failure happen again? And this is just as bad, or actually worse, than a spurious trip. Dangerous detected failures are not only used in the safe failure fraction, which we'll take a look at later, but they're also used in the PDF average calculation. And this calculation has 9 key variables, but it has a lot of different inputs that includes the dangerous detected failures. It includes the system architecture, and you can do all of calculations using modeling software such as Excellentia. We're actually going to take a look at a quick example using Excellentia later today as well, so you know exactly how Excellentia can help you with both the dangerous detected and the safe failure rates. This is an example of an actuator certificate, and one of the issues with this is you're given a dangerous failure rate and you're given a dangerous detected failure rate, but you're not given a safe failure rate. And if you're just concentrated on having a piece of paper to say, oh, your actuator that you bought or that you produce needs SIL 3, here you go, great. You can do this route. But if you're going to do calculations with the numbers, if you actually want to make sure you're going to get the risk reduction that you need, you're going to have to not only have the dangerous detected, but the dangerous undetected and the safe failure rates as well, to really know what you're getting into when you're purchasing or when you're putting in these final elements. So what does the standard say? The standard directly says that hardware must show compliance via, you can either do architectural constraints on hardware safety integrity, or it meets the safe failure fraction or Route 2H, which we'll dive into both of those options in a little bit, or the requirements for probability of dangerous random hardware failures. So that would be such as a low dangerous undetected failure rate. So this is pulled directly from the standard, and it talks about hardware compliant routes. And it's talking about the highest safety integrity level can be claimed for a safety function is limited by hardware safety integrity constraints, which shall be achieved by implementing one of two routes, either Route 1H or Route 2H, where Route 1H is based on hardware fault tolerance and the safe failure fraction concepts, and we're going to look at the safe failure fraction next, or Route 2H, which is based on component reliability from feedback from end users, increased confidence levels, and hardware fault tolerance. And we're going to look at how Route 2H is similar to Route IEC 61511 for specified safety integrity levels. And we'll go through what those mean. One thing to note is it goes further to explain that if Route 2H is selected, then the reliability data uncertainties shall be taken into account when calculating the target failure measure. So that would be the PFD average for low demand mode or the PFH for high demand. And all systems shall be improved until there is a greater confidence greater than 90% that the target failure measure is achieved. So looking deeper into Route 1H is the safe failure fraction method. And the safe failure fraction is defined as the ratio of the safe failures plus the dangerous failures detected by automatic diagnostics total average failure rate of the subsystem. It then is the percentage of failures that can be considered safe. And this definition is defined for a single channel, so that meaning no redundancy, a 1 out of 1 system. What happened in 2010 when the new standard of IEC 61508 came out, previously the safe failure fraction included no effect failures in the numerator. The problem was people were kind of cheating the system. People were adding all sorts of extra parts or extra ways of failing to include, to be counted as no effects to increase their safe failure fraction. But that didn't mean that it was actually a safe failure. It didn't mean it was actually a safer system. It just meant that they had more no-effects failures. So, to make sure that people weren't cheating anymore, they removed the no-effect failures from the equation. But in doing so, created a problem for simple mechanical devices, or basically most, or if not almost all, final elements. So to make up for the final elements, or the simple mechanical devices, not meeting the safe failure fraction requirements, usually even for a SIL 1 application, they had to create a different way of assessing simple mechanical devices, and that's how they came up with Route 2H. And we're going to look at that next, but to be able to get the safe failure fraction, you have to have the safe detected, the safe undetected, the dangerous detected, and the dangerous undetected failure rates to enter into this equation. And the way to get those numbers is called an FMEDA, a Failure Modes, Effects, and Diagnostic Analysis. So when you plug those into the equation, you can, from the FMEDA, which are listed on the back of certificates or in the FMEDA report, you can then get your safe failure fraction. And as you can see, I kind of jumped ahead a little bit, but when people look at the safe failure fraction, they'll look and see, well, how can I use this if I have a simple mechanical device? What if I'm doing everything right? I'm doing proof testing exactly when I should be doing it and how I should be doing it. I'm doing leak detection. I'm doing partial valve stroke testing. And I can't even make a SIL 2 or even a SIL 3 because of safe failure fraction. There aren't, if you're just looking at a valve alone, there's not a way to have automatic diagnostics. So safe failure fraction could be 0, or it could only be 30%, and that looks like that you aren't having a safe system, you're not doing things correctly, when actually you could be. And that's how Route 2H was introduced. So once again, Route 1H is a safe failure fraction calculated by 2 different tables in the standard, and they are used to determine the minimum hardware fault tolerance, which gives you the minimum redundancy needed for a given SIL level for each element. Or you can do Route 2H, which are failure rates based on a method that gives 90% confidence in the results. So there's no longer the safe failure fraction, and the minimum hardware fault tolerance, or the minimum redundancy, is determined by a set of rules set by the standard. To qualify for Route 2H, you have to make sure that you follow the different rules for it, including reduce architectural constraint based on the confidence of 90% in the quality of the failure data. And 90% confidence is more than just a statistical analysis. It actually means that you need to have a high quality data collection system. You need to make sure you're accounting for all of the failures, tracing them back, figuring out why something happened, and not just say, oh, we think we had 2 failures last year. It needs to be more than that. And when you're comparing the number of hours for different valves or different actuators or parts in those valves or actuators, the application and the environment conditions must be similar. You cannot have a ball valve or a gate valve say in a clean environment, in a cabinet, you know, somewhere, and it's never going to be stressed too much, and say that, well, this is running great here, so I'm going to take that gate valve and put it subsea and expect it to behave the exact same way in a corrosive environment and with dirty particles flowing through it. That's just not reasonable. So the standard does say that the applications and the environmental conditions must be similar if you're comparing two devices for Route 2H. Once again, we take a look at the standard, and it's saying once again that you can base it off of Route 1H, which is the hardware fault tolerance or safe failure fraction, or Route 2H, the component reliability from feedback of end users. Now this is where we get a little more in depth in Route 2H, and it tells you that it's the minimum hardware fault tolerance for each subsystem of an EEPE safety-related system implementing a safety function of a specified safety integrity level shall be as follows. It tells you that in the following clause, unless otherwise specified, the safety function may be operating in either low demand mode of operation or high demand or continuous mode of operation. That's again one of those application restrictions. You need to know if it's always been tested or put in a low demand or a high demand application. It needs to stay that path. Then it goes through the different hardware fault tolerances for each SIL rated condition. And it comes out to this chart. This chart is very similar to the IEC 61511 proven in use for field device tables. As you can see, it no longer makes you look at the safe failure fraction. It is identical to the 61508 type B table for safe failure fraction 90 to 99%, and if you see that 90% is once again repeated, or the type A table for a 60 to 90%. So once again, that 90% confidence factor is not something that they just made up. It's something that has always been in practice, even in the previous editions of the standard. And this is what the prior use IEC 61511 architecture constraints prior use table looks like. As you can see, it's almost exactly the same. It just has a difference for SIL 4, which, if you know much about functional safety, you know that SIL 4 is kind of like a unicorn. It doesn't break apart into type A or type B applications. There is no requirements for the safe failure fraction, and it's identical once again to the IEC 61508 type B table for 90 to 99% and the type A table for the 60 to 90%. After looking through the standard, you can see that there were some guidelines on what to do or how to do Route 2H, but there were some gray areas. There were a lot of things left out of the standard. So we have made our own criteria, and being a conservative company, we came up with conservative rules to make sure that we weren't doing something that could potentially put somebody into danger. So to meet the exida criteria, you have to meet all of the criteria of the standard along with 100 million operating hours per product type, documented traceable field failure studies, field operation for 1 year or longer, and a FMETA done with 2H components. And what that means, during an FMEDA process, we break apart the device per each line of the bill of materials. We look at every single nut, every single bolt, every single O-ring or stem, and we make sure that it is something that has been proven in use or proven in history. This isn't a new type of O-ring with a new compound that has never been tried in the field before. This is only tried and true components and technology. And that's how we can use each component and compare it to our database, do a FMEDA with those components, and make sure that they align with the components on our database. From there, you receive your safe and dangerous, detected and undetected failure rates. And this is actually what the 2H database, just as a little screenshot, looks like. We break each component down by a component, subtype, and use categories, along with the failure modes. We have our failure rates, our failure rate distribution, and our different environmental profiles. So we look at the environment and the application for each component. If they are indeed 2H, they get a check mark when they receive over 100 billion operating, or 1 billion hours for each component. If the FMEDA is done and every component on the bill of materials is checked 2H, then the device is checked 2H. When we went through and took a look at all of our failure component data, we were able to make a big database and spreadsheets, and we saw that, well, at one point we had, when we started, it was about 50% of the components on the mechanical database were covered under 2H. Now it's probably between 70 and 80% of the components are considered 2H qualified. And we took a look at all of the operating hours collected that we have analyzed, and it is well over 100 billion operating hours. So this is a screenshot of Excellentia, and I just wanted to quickly show you what some advanced modeling would look like and what can be found with advanced modeling. As you can see, we break a final or a sift down into a sensor, a logic solver, and a final element group. We are able to then see the PFD average for each of those groups, the mean time to fail safe in years, the SIL level of the PFD average shown, the lowest one, and if there's any SIL limits. We also are able to look at the risk reduction this SIF would contribute, along with what the main contributors of the PFD and the mean time to fail safe are. In this example, just using some generic numbers, you can see that the logic solver mean time to fail safe is 384 years. Well, that's pretty good. That's great. The logic solver is 7.43 years, and the final element is 998 years, mean time to fail safe. So you can find which part is misbehaving or giving you spurious trips often, and you can see if you can lower that by choosing a different part or doing proof tests more often, there's different ways that you can use the final or the Excellentia tool or any advanced modeling tool to play around with it. Say you need a larger risk reduction. Great, we can change that. Say you need a different PFD average or a different SIL level. There's ways that you can pick and choose. You can change your architecture. You can change the product type or the product, the people that make the product, and see how you do better or worse in different situations. So if spurious trips or safe failures are something that you're concerned about on your plant, there are ways to help you reduce those. So just to reiterate, you know, safe failures aren't always a good thing, but calculating them can provide very useful for your company. So if you are going to receive a certificate or a device that is SIL rated, you care about the dangerous failures, but you also care about the safe failures. The dangerous detected failures will affect your plant just as much as the spurious trips. Simple mechanical devices or final elements can still participate in a SIL rating even if they have very low or even no safe failures by using Route 2H. And mostly exida and functional safety certifying bodies, they don't want you to get spurious trips almost as much as you don't want them. But if you do get one, please, please, please don't bypass your safety system. There are much better ways to solve that problem. So I'm going to take a moment for any questions. And if you think of any later on, please feel free to email me. I will get to them as soon as I can. The first question we have are, okay, these are more common sense questions. If anybody has any questions, there we go, I have one. They were asked if they would like to know an example of safe failures that were detected. Well, it depends on really the type of system that you have in place and what automatic diagnostics there are. But there are ways to I'm sorry, I'm getting more comments coming in. If the automatic diagnostics can detect a spurious trip beforehand, it depends on what type of system that is really in place, what type of SIF there is. So that's all for right now. If you have any other questions, please feel free to email me, and thank you for joining and have a great day.